Just in the meantime, if I may share a little idea, I was following the Discord chat earlier this morning, and I mean, there was talk about processing checksums in the data to make sure that the data is received and in the right order. And I had this thought, if we were to, an alien was to send a message, would they also include some sort of checksum or some sort of encoding or some sort of way of making sure that when the message was received, it wasn't like misinterpreted? Almost like, if an alien sent out a hello world, we're here and friendly, but if something got misplaced and it was misinterpreted and they said, we thought they said, hello, we're here, but we're coming to get you, sort of thing. I wonder if that's sort of been, have you had any thoughts around that?
Yeah, I do have some thoughts on that topic. So there are mathematical codes which can be used for detection of errors. They are called error detection codes, and the checksum is one of them. And they are also error correction codes, which not only give you the capability to detect errors in the message, but also to correct for a few of them.
Right.
When you're thinking of an alien trying to send some information to us, then the difficulty is that we don't know the code that is supposed to be used. So either it is something which is very simple, and the most simple error detection and error correction code is repetition coding, which means you send the same message multiple times, or sort of the intuition or the knowledge about the code that is used is communicated to the receiver by transmitting several messages so that you can try to reverse engineer and understand how the code should work. For example, if you choose to use a CRC, you might send a short message, an empty message, and then you might send your whole message. But that's a difficult notion, right? Because it boils down to, are mathematics universal? Could an alien intelligence have our same knowledge about coding theory? It's a very good question.
Or even if our approach is too simple for even them, if they're more advanced and they've got a better way of doing it or something. It just occurred to me actually that, without some sort of error checking and validation, then we could potentially misinterpret a message, just like we could maybe, misread data from the TGO satellite. It could mean that we were missing the actual underlying meaning of a message. Just maybe a little bit more philosophical than from a data processing perspective.
Hi, I actually had a view regarding the whole project. It seems to me that it's the message more resembles more like an intercept rather than a direct message to us. Say, as you guys have been discussing, it seems to me that any contact type of message wouldn't involve such a encryption mechanism and the awkwardness of any possible deciphering of any message. I mean, it could happen perhaps after an initial communication had taken place, and then you were sending maybe more advanced data. But I always have envisioned it something like the very first Frank Drake type Arecibo message that he sent. The simple digital zeros and ones generating the sort of raster scan type picture, and something simple like that could be relatively decoded without any very amount of sophisticated message sort of deciphering. So I realize this is not necessarily perhaps what would happen, and it was stated that it was more of an art project or something along those lines when it was envisioned. So it seems to me more like an exercise in code breaking. What you might want to do to a signal from I don't know, a foreign nation satellite that you might want to decode the data from, and not necessarily something that would be received as a SETI type signal. But anyway, that's just kind of my view. I'm not actively working on deciphering because I don't have the background to be able to do this deciphering, although I do follow SETI and radio astronomy. Actually, amateur radio astronomer detected the 21 centimeter hydrogen line in my backyard with a very simple setup. So you might recognize my login picture there, especially Wael or Farah. You might recognize that.
Yeah, it's relatively known.
Yeah. Well, that was my own picture from the visit up there at the Hat Creek a number of years ago, which is a wonderful experience. I really enjoyed that. And so, like I said, I've been following the field for quite a number of years, even though I'm not necessarily in the communications field. I'm actually a molecular biologist, but I'm very interested in astrobiology. So obviously SETI fits in. But anyway, I just thought I'd drop in my views on what I thought the message sort of signified. I don't know if that was kind of my point.
I think that is a very good point, and it's also a point that many people have raised in Discord, that if we were to receive an alien message, it would probably not look like TGO signal. And the explanation why we have TGO signal for this project is basically because of technical constraints. So we have sent a message essentially in the only possible way that is possible to send with this satellite. It turns out it's a little bit complicated. It involves going through several spacecraft communications protocols, which people on Discord have been great at figuring out and decoding the multiple layers. But it was basically that restriction. Spacecraft are usually not very flexible. They tend to use simple computers, old computers and protocols. So we met with ESA and spoke about how to transmit a message or a file with binary data from TGO, and this was basically the only option. There was actually a second option we considered, which was using the UHF system on TGO. So TGO has the electro radio from JPL. This is used to communicate with the rovers on the surface of Mars, and it transmits at 435 megahertz, I believe. It's around 400 megahertz. And if we had used that radio, probably we would have had more flexibility in how to encode the message at the radio frequency level. However, it turned out that none of the observatories that were participating really had the capability to receive in UHF. It's outside of the frequency coverage of the Allen Telescope Array. Medicina had a strong radio frequency interference at that particular frequency, and I'm not sure what the problem was with Green Bank Telescope. Maybe the UHF receiver was out of service or something. So that's the reason we use the normal X-band signal from TGO. On that respect, I wonder, Wael, what are the usual notions about how an extraterrestrial signal could look like at the radio frequency level, and how we could possibly detect those?
You mean compared to an interference signal in general?
Compared to TGO, compared to the more complex radio frequency communication protocols we use, I guess from a SETI perspective, we expect an initial alien message to be something relatively simple. So if you could give some details on that topic.
Sure. Yeah, so in general, what we are concerned with, and here I'm putting a radio astronomy hat on and not an engineering hat on, what we are interested in is finding a signal in total power, finding a signal that is non-natural in its essence and its production. And here, like many. So in astronomy in general, there are so many events, catastrophic events in terms of, stars going supernovae and stars, merging into each other, all of these events would create radiation. Now, these types of radiation, we have models for, right? We have physical explanations for, right? These are, extended sort of emission, continuous emission over, broad frequencies. Maybe that continuous emission has some sort of a spectral feature, at some point during this supernova event, for example, the peak of the emission starts becoming, sort of going down in frequency as time passes and so on. So we have physical models explaining this kind of emission. Whereas what we are trying to search for, at least in the SETI context, we're trying to search for a signal that cannot be produced by nature. So nature cannot, for example, produce a signal that is a sub, let's say, 100 hertz level, right? A signal that is compressed a lot in frequency. There is no physical mechanism that can create such a signal. So from a SETI, and this is one of them, right? From a SETI perspective, this is what we are concerned with. This is what we are this is what we're trying to search for. We're trying to search for a signal that cannot be produced by nature, doesn't have a physical model, and it sort of that's our only way to try and differentiate, the so many sort of radio emissions from the cosmos from something that can originate from a technologically capable civilization. Now, I do get asked this question a few times, is, can we decode that signal if there's a signal being sent? The question is, we do not know. What we're really concerned about, at least again, from a radio astronomy perspective, is to just find the signal, right? And then, people like Daniel here on the call and everyone else can, figure out if the signal is, there's a message encoded in that or not. But at least the initial detection is what we are really, really seeking, at least in our case. Does that answer your question, Daniel?
Yeah, I think it's a very good answer. And you made a very good point that signal which is very narrow in bandwidth should be artificial, electronically generated, because none of the high energy phenomena, astrophysical phenomena, produce such kind of frequency or spectral representation. And in the case of TGO, of course, we have the spacecraft electronics. In the case of another artificial signal, we would also have a different type of electronics. But there is a quote I like very much from my friend Phil Karn, which was employed at Qualcomm for many years. And he says that any sophisticated enough communications mechanism is indistinguishable from noise. This is a play on the quote that any sufficiently advanced technology is indistinguishable from magic. Mm-hmm. But there is some background to it. And what Phil really means by this notion is that mathematically, when you want to encode information in the way that is most efficient to transmit through a radio frequency channel, and I spoke before about error correction and error detection codes, the signal is going to be spread out in frequency, and the higher the data rate you want to send, the more bandwidth you are going to be occupying. So for detection of that signal, that already gives a challenge and some limitations, because as the signal is spread out in frequency, when you want to detect it, there is more noise below the signal. And it's also easier to mistake this signal for natural process. For example, the hydrogen line is several kilohertz wide. We will see TGO digital sidebands are also several kilohertz wide. Of course, the difference is the hydrogen line has a kind of irregular shape, and it depends on where on the Milky Way you look at. And the TGO sidebands are a very nice sync shape.
Right. So you're speaking on the 21 centimeter line as being spread out, and I gather that's from the Doppler shift. Movement of the movement of the different hydrogen clouds, either towards or away from us and spreading the signal out by Doppler, which actually brings out a very good point. And I've thought about this and discussed it with other people at times, that the ideal signal, as was mentioned, would be a very narrow bandwidth signal that would be totally artificial. But then looking at the progression of communications here on Earth, we're moving away from these discrete, very relatively narrow bandwidth signals and going, as you described, Daniel, with very wideband sort of digital communications for the amount of data that's being transmitted. And so the only things that are left, I mean, even the TV stations are fairly wide bandwidth. So possibly about the only things that are left that are relatively narrow bandwidth are things like radar systems that might not be encoding signal. And so I've wondered if we were to intercept communications from an intelligent civilization, if they were even as advanced as we are, it would just be a very broad spectrum noise that would be emanating from the planet. And so that might be more difficult to distinguish than the earlier notion of a directly being sort of a narrow bandwidth, sort of initial communication type of message. But yeah, I think that's something to consider in terms of what might be detectable.
And I'll add to that is so in general, the way we do SETI is via two things, or at least in a conceptually, we try two different approaches. One is trying to search for a deliberate signal, a signal that is being sent deliberately either to Earth or omnidirectionally from the source. And two lines of we try to search for signs for technology on a planet somewhere. So I guess those two sort of things, like as you had mentioned, I mean, we're moving away from narrow bandedness and how our communication happens. But if you're trying to conserve energy and send a beacon, right? If we were to build something and send the beacon, let's say, aimed at the center of our galaxy, we'll try to make it as efficient as possible, and being as narrow band as possible makes it makes it more efficient for us to actually focus enough energy to actually to send. And so that's kind of the way that we are you can think about that. So narrowband signals are still something that would be interesting to just search for in general, just because it's to produce.
One possibility is, of course, the optical OSETI, and using things like lasers, which can definitely have huge amounts of power and can be very direct in terms of the beam. Whereas even at radio frequencies, you have to have huge dishes to be able to allow for the wavelength to be focused to a fairly significant directivity. But in any case, yeah, I've thought about that, and then the option of actually sort of listening in on extra solar type of planets that might be having communications that would be detectable. But yeah, a directed message would obviously be focused, as you said, with something with the narrow bandwidth that would sort of be the best use of the power available. But I mean, we have had things like, unfortunately, the Arecibo telescope is gone, but when it was doing for example, the radar astronomy and imaging asteroids, that had to have been a significant signal that was being beamed out, not directionally at any one spot, but I mean, if anybody just happened to be in line with that transmission, it would certainly be a fairly discrete signal that would be identifiable as being artificial. And I guess that's still being done to some degree now with the Deep Space Network and bistatic radar, with Greenbank being the receiving end on some of these imaging projects that have been carried out on some of the sort of near Earth approaching asteroids. So that would be a type of signal, perhaps, that would be sort of detectable from some other civilization attempting to do similar things. But it wouldn't necessarily be directed at Earth, but it would just have to, it might be something like that. It was picked up at the Wael signal. It might have been something like that, not directed at Earth. We just happened to be in line at that moment. Always wondered what the outcome of that signal was, what the origin. I guess to this day is still a mystery. I did have one question before I kind of sign off for a bit. Daniel, you mentioned the UHF comms that are on Mars. I was kind of aware of those. As a matter of fact, I think I can't remember which Mars probe that was sent up, and it was transmitting on the UHF bandwidths, and it was for ham amateurs and people using amateur solar ray astronomy detection to see how far away they could detect it. So I'm just curious, would that signal have sufficient power and directivity? I mean, I can't imagine that the satellite has an antenna that can beam, as you said, around 400 megahertz, a very narrow beam to Earth. I can see how it can do communications with Mars, but I don't know if that signal would be detectable at Earth. So I don't know if either one of you have any further comments about that.
If detectable, it would probably be detectable with difficulty, because the UHF communications are intended for relatively short range communications between the orbiters and the ground assets. So that means a few thousand of kilometers, at most 10,000 kilometers. And Mars is between
millions of miles.
Millions of miles. I'm saying from memory, 50 million kilometers and 400 million kilometers. So it's several orders of magnitude above that. Communications at the UHF has compared to X-band, has the difficulty that you need to have much larger antennas to achieve the same directional gain. And that's also the reason why it's used for these short range communications, because in UHF, the rovers do not need to accurately point their antennas to the orbiter. So to give you an idea, during the Mars 2020 mission, the descent stage was transmitting on UHF for the same reason, because during descent, it's really difficult to point a directional X-band antenna back to Earth. And GBT was listening, and also the Effelsberg telescope in Germany. Those are both 100-meter telescope classes. The signal was, I believe, a pair of tones. And coming back to the notion of what's the most simple communication mechanism you can have, when you have a spacecraft which is either very far out as New Horizons, or it is limited in the power it can transmit because it's in hibernation state or something like that, you just transmit a pair of tones, and the frequency difference between those tones tells you something about the status of the spacecraft. And DSM people call them the happy tones if everything's going okay, or sad tones if not, and they might have a bunch of those to encode different conditions. So in this case of Mars 2020, the spacecraft tones were received with GBT and with Effelsberg, and they were rather weak with those telescopes. So I'm not sure, we never looked at the technical details of whether we could have made the UHF transmitter on TGO work for this project. Perhaps with GBT and transmitting really slowly, it could have been possible, but it's a far stretch.
Yeah, that's what I would have guessed. So anyway, well, I hope somebody else chimes in and gets the signal decoded soon. I'm interested in what the message is. Thanks a lot.
You're welcome. Okay, then I guess I'm going to share screen and share a few things which are rather basic, but probably useful, especially for those of you who are not specialists in signal decoding. So probably the main question I've seen in Discord is, what are these SIGMF files? what can I do with them? How do I open them? So SIGMF files are basically raw radio frequency recordings. This means that the data we represent is the voltage on the antenna sampled over time, and there are 1 million samples per second because we want to represent a 1 megahertz bandwidth, because that's pretty much the minimum bandwidth in which we can capture the complete signal from TGO. And then the file is a raw file, so that means it's a sequence of 8-bit integers, and they are complex. That's a mathematical trick which is often used for signal processing. So you have the real part, imaginary part, real part, imaginary part as 8-bit integers, and you can read that with almost anything you can imagine. You can read it with Python, NumPy, you can read it with MATLAB, you can read it in C, in any other programming language, or even you might fire up a hexadecimal editor and look at the numbers on your own. Of course, that's not very useful on its own. The main reason you want to open this kind of file is to do some calculations or signal processing with it. But anyhow, the most basic way I think of opening these files is with a web application which is called IQ Engine. This supports opening local files. So you have the SIGMF files on your computer, you can use this option to open them. This, at least for me, this only works on Google Chrome. This is Firefox. It doesn't really work. I click here, it doesn't do anything, but in Google Chrome it works. I'm using Linux. I haven't tested in Windows, but I guess it's the same. So this will open the files locally. It will not upload anything on the cloud. It's just an cloud application of sorts. Mark Lichtman, who is the author of IQ Engine, was kind enough to upload the data to the cloud. This uses Azure as an storage. So it's not even necessary to download the files to your computer. You can click here in Browse. And there we have the 4 recordings from the telescopes. You can click on one of them. And then what appears in one moment, because here is the computer doing the calculations. I think it's JavaScript. So there's a fast Fourier transform, and the fast Fourier transform is used to transform from this time domain representation to frequency domain representation, which is often more convenient. And here we see the frequency axis. So this is 0, this is the middle. This is minus 500 kilohertz. This is plus 500 kilohertz. So there's a total of 1 megahertz bandwidth. And here we represent power versus frequency and time. So time is the vertical axis. This is the beginning of the recording, and then time goes down. And this is just the small piece of the file, so we can scroll down in here, and it will load up on demand, small snippets of the file. So what we can see is a narrowband signal in the middle. This is quite similar to what Wael was describing as something which can be only artificially generated, and also very simple to detect because it is a pure sinusoidal RF waveform. And this is called the carrier of the signal, or the residual carrier. And it's used for phase synchronization in the receiver, because in any kind of digital communications, the transmitter and receiver need to agree on basically some time intervals. So you can imagine that bits are essentially transmitted at regular timing, but the transmitter uses its own clock, and the clock is not embedded in the signal. So the receiver needs to monitor the signal in some way and to synchronize with the transmitter clock. So that's what this is used for phase synchronization with the transmitter. Since this is an X-band signal, which goes out at 8.4 gigahertz, synchronizing to the signal means achieving a time synchronization of approximately 10 picoseconds. And 10 picoseconds is really precise. So that's the reason we have a dedicated carrier for that. And it also makes the signal easier to spot in case there is some problem with the spacecraft transmitter. Maybe the antenna is pointed away from Earth. Still, we have the carrier, which is easy to detect on the spectrum. And then we have the data, which is here and here. These are called subcarriers. Subcarriers are used to push the energy of the modulation away from the central residual carrier so that the digital information does not interfere with any attempts to synchronize with this subcarrier. And this looks more or less as the kind of broadband digital communication signal I was mentioning. This is about 100 hertz, I believe. Yes, the tick marks are 100 hertz apart. So this would be more difficult to detect if the signal was weaker. It would be buried in the noise, and it could also be mistaken by a natural process. But on the other hand, you can see, for example, in the frequency domain, I can toggle cursors here and go to the frequency domain. This is relatively smooth and mathematically perfect. In fact, it is a sync function, whereas something which is natural would have a more complex shape to it. Okay, so this is one way in which you can explore the signal, but it's fairly limited. Essentially, you are able to look at power and frequency, so power versus frequency and time. Another tool you can use for the same is in Spectrum. This works well on Linux. I'm not sure if it can build for Windows or Mac OS. Probably it's possible, but fairly complicated. And it gives you more or less the same capabilities as IQ Engine, but locally, so you can move through the waterfall much faster. I have it open here, so it's nearly the same, but time is now horizontal. And I can click and drag with my mouse, and we see that it's the same signal all along. We can also change the FFT size, for example, to zoom in frequency and have a more detailed look at the central subcarrier. And we also see some signals here. I believe these are artifacts caused by the receiver. This is GBT recording. And something that needs to be kept in mind is that the radio astronomy receivers are intended to receive rather weak signals. So when you have a really strong signal, such as the TGO signal here, you might have saturation on some of the digital stages. You might have intermodulation on analog stages. And as Larry Morgan mentioned on the live stream, there were some problems at the beginning of May with the GBT local oscillator. So maybe this is a theater of the local oscillator. It's not a theater of the TGO signal because it's not present in any of the other recordings. The Medicina recording has some pair of tones similar to this, but the frequency separation is not the same. So they cannot be the same. Still, tools like these are fairly limited to give you a good overview of the signal. So what I did with my own tools was a single picture with which represents the whole GBT recording. So this is 1 megahertz in vertical, and this is the approximately 35 minutes that it lasts. And again, we have power encoded in color. So yellow represents the most powerful pieces of spectrum on time, and this dark blue is the weakest. This is just caused by the digital filter we use to make these 1 megahertz files, because usually GBT will record at using channels of 3 megahertz. So there was some cropping of the spectrum to make this. So what's going on here? We can see a couple things which were not obvious before. The first of them is that the signal is going down in frequency. This is obvious both in the carrier and in the data sidebands. And this is caused by the Doppler effect. So the TGO spacecraft is in low Mars orbit. That means that it takes about a couple hours to go around Mars. And during a fraction of the orbit, it's behind Mars, so it cannot be received from Earth. During another fraction of the orbit is in front of Mars, and it can be received from Earth. So speaking about the assigned space live event, the exit from Mars occultation was about 1845 UTC. The beginning of the recording is a couple minutes before the message reception on Earth, which was 1916 UTC. And the message was transmitted from the spacecraft 60 minutes before that. So the light time delay between Mars and the Earth was about 60 minutes. I'm giving this in detail because this interesting thing will have something to do with that. So yeah, basically as the spacecraft is orbiting Mars, because of how the Doppler works, because of how the geometry of that orbit works, the frequency goes down. And that's what happens here. I should also mention that frequency drift, having a signal that moves in frequency versus time, is a tool which is commonly used in SETI to distinguish local radio frequency interference from anything that comes from space. Because something which is a local RFI will usually be static in frequency, and something which is from space, be it either RFI, meaning signals from any of the many satellites we've launched, or an extraterrestrial signal such as the ones we're looking for in SETI, will have Doppler effect, if only because the Earth moves. So anything from space will have the Doppler effect due to Earth rotation. And if it's on the surface of some planet, it will also have the Doppler effect from that planet. If it's in orbit, it will also have the Doppler effect to the orbit. So there's some Doppler effect to all signals coming out from space. What else can we see in here? It's rather faint, but we can see some extra lines. I'm going to zoom in. So this is the artifact from GBT. But then here we also have some additional narrowband signals. These are the telecommand signal from Cerberus Station in Spain. So during the event, ESA was tracking TGO as they do normally. And what they do is to send out a telecommand subcarrier, even if they do not need to send any telecommand information, they will always send the telecommand signal, so that if the need arises to send the telecommand, then the signal is already ready. The spacecraft has synchronized to that telecommand signal. So to speak, the telecommand channel is open in case there is a need to send the telecommand. You can think of those old telephone switchboards where you connected with cables, different jacks to get telephone calls across. So this is the same. This is opening a physical communications channel in case you want to send out anything. I believe no telecommands were sent during this event, but they opened the telecommand channel just in case. And in here you see the signal which has been transmitted from Earth, and it takes 60 minutes to go to Mars and 60 minutes to return. This telecommand appears right after this funny shape. And this funny shape is caused by something which is called an uplink sweep. So what they are first doing when they start tracking the spacecraft is to transmit a an uplink signal, which looks quite similar to this one. It also has a narrowband carrier in the middle. And they will sweep through the spacecraft receiver frequency. And when the spacecraft receiver sees the uplink signal, it will lock to it and it will follow its frequency. So here we are actually seeing the frequency that has been originated in Earth is received by the spacecraft, and it's replicated, multiplied in frequency, because the uplink is 7-point-something gigahertz. So it's multiplied in frequency to generate this 8.4 gigahertz and sent back to Earth. And this is the sweep. This is the frequency sweep they do with the telecommand when they start transmitting. And they do this for two reasons. First, to pass in front of the rest frequency of the spacecraft receiver. And the second is to have a visual, very clear confirmation that the spacecraft is locked. If the spacecraft follows the sweep they've done, it is locked. If it doesn't follow it, then it's not locked, and they need to figure out what is the problem. Give you lots of detail on this, because just because of a matter of chance, it more or less matches the beginning of the message transmission, or it seems to be related to the message transmission in some way. It is not. I think what's happening here is that when ESA sees on their ground station the signal from TGO for the first time, because it has exited the occultation, so it has exited from behind Mars, they start transmitting this telecommand signal. So then what happens is 32 minutes after that, you see the effect of that back on ground, because the signal needs to travel to Mars and back again. So if anyone takes pen and paper and writes the numbers, it's something like 1846. The spacecraft exits occultation as seen from Earth. So that means that actually exit from occultation on Mars was 16 minutes prior to that. And then 16 minutes after that, the signal from the spacecraft arrives to Earth at first, and ESA is starting to send this telecommand signal. And also at the same time, more or less, because it was 19 UTC exactly, as Johannes said on the live stream, TGO is transmitting the message from Mars. And then sort of the telecommand signal and the message cross on their way between Mars and Earth. And at 1922, I believe, this is this event, we see the sweep, the Z, as someone on the chat is mentioning. And we also start receiving the message at 1916. So there is no real relation between the two. This is just some curiosity about how ESA runs their spacecraft operations. What else is on this picture? Nothing of interest, I believe. So what else did I want to say? Yeah, there is this workshop I made a few years ago. I shared the link very soon during the decoding process, because the main goal of this project is not to spend so much time fighting your way through decoding spacecraft communications protocols, but rather finding the message and giving both a technical and artistic interpretation of the message. And hopefully there are some very clever people in Discord who are also somewhat familiar with spacecraft communication, who have gone fairly quickly through the first stages of decoding all these spacecraft protocols, which we needed to have in there, because that's the only way in which TGO can transmit a file back to Earth. So this workshop is fairly long. It's also fairly detailed. Here I'm going to give a much shorter overview, and a much more basic overview. This was a workshop in the GNU Radio conference. So some background about either GNU Radio or signal processing or mathematics is assumed. Here, I will assume no background. Also, there are some GNU Radio flow graphs in this workshop. You can modify those to decode TGO signal, but I have preferred to use one of my newest flow graphs because I've improved how I do a few things throughout the years. Today, I will be using a modified version of my JUICE flow graph. This is from 1 month ago. So in case you're not aware, JUICE is the latest ESA deep space launch to Jupiter and the Jupiter icy moons, and it was launched in April. So something I will mention is most ESA spacecraft are very similar. In deep space design in general, when something works, you don't reinvent the wheel, you don't change things for no reason. Having the same system being flown for 20 years or for 10 years means more reliable rather than old and we want to change it. So the same kind of things that work for JUICE work for Solar Orbiter, which was the spacecraft I used in the workshop, or for TGO, or for pretty much any ESA spacecraft unless it's really, really old. So yes, I'm using GNU Radio for this, mainly because that's the tool I use the most often. But there are other people who have used SIGDigger or SatDump, and any of those can be used. The authors for SIGDigger and SatDump are both in the Discord channel. So if you want to use any of those tools, my best advice is try those out. And if something doesn't work, you can just reach out in chat to Batch Drake Gonzalo, who is the author of SatDump, of SIGDigger, and AANG23, who is the author of SatDump. So, okay, here I have the GNU Radio flow graph for decoding TGO. It's a modified version of the JUICE flow graph, and I've needed to change a few small things, mainly the baud rate or symbol rate and the subcarrier, because depending on how much data you want to transmit, you will use a different baud rate and subcarrier rate. And for the Assigning Space project, what we did is to study link budget with ESA and adjust the data rate so that the Allen Telescope Array, which is the smallest telescope, was able to receive the signal without any problems. And in fact, the Allen Telescope Array had a link margin. So that means how much extra SNR you have of several dBs. And I hear radio interferometry station on the Azores Island also received the signal with short notice, and they managed to decode all the telemetry with a 13.5 meter antenna. So even a station smaller than the Allen Telescope Array could be used for this event because ESA had dropped down the data rate from what is normally used on TGO. So yeah, how to figure out the baud rate and subcarrier, that is explained with a lot of detail on the workshop, and people have also figured that out on Discord and posted the values, I believe. So yeah, in GNU Radio, what you have is blocks. Blocks represent signal processing steps or operations, and you connect them so you can think of the signal as flowing along the connections and going from one block where some operation is done to the next block and so on. And in such a way, you build a complete receiver or transmitter for the kind of signal you're interested in. Not going to explain what all the blocks do, but at least I'm going to use them to kind of tell a story of what are the steps needed for decoding these kind of signals. And this is widely applicable to any deep space communication signal. So first we have the file source. There were also a few difficulties with people trying to open the SIGMF files using the SIGMF file source for General Radio. Unfortunately, it doesn't support complex 8-bit integers. We use complex 8-bit integers to save on space. It makes the files half as large in comparison to using 16-bit integers, and it doesn't lose much precision. And for 8-bit integers, you need to use the file source and you need to use the output type byte. And as I mentioned, the SIGMF data files are raw files, so you can use them with a regular file source. The SIGMF meta files are JSON metadata. So by looking at those really with any text editors, you will learn that the sample rate is 1 million samples per second. I also have needed to set that there, and that the samples are complex 8-bit integers. So going further, an important component in the decoding is the PLL. The PLL is used to log to the residual carrier. So we have this carrier in the middle. The PLL tracks the frequency and phase of this. And we will see graphically how this looks like when I run the flow graph. To run a flow graph, you press this play button. Then what we do next is to kind of grab the digital information on these sidebands. So we do some frequency translation and filtering to focus on this part of the signal, because that's where the data lives. And that is accomplished by this frequency translation and decimation filter. The next thing we need to do is to recover the symbol clock of the spacecraft. I mentioned before that in any digital communications protocol, symbols are transmitted at regular intervals, and those intervals are decided by some electronics on board of TGO. Of course, we do not have access to the electronics on TGO. There is no cable connecting the receiver on ground to TGO. So the only way to know what that clock on the spacecraft was doing was to observe the signal and to derive what are the transitions between the digital symbols. And that's what this symbol synchronization block is used for. And finally, there is a Costas loop. So what the Costas loop does is when we are translating in frequency this sideband, we might be making a small frequency error. So the Costas loop looks at the signal, recovers the suppressed carrier. So this doesn't have any carrier like this. But if we were to raise this to the power 2, we would recover narrowband carriers such as this one. And by the way, that's an operation you can do in IQ Engine. It supports writing in there some simple Python code to do simple operations with the data, and you don't even need to download the files to your computer. So the Costas loop recovers the frequency error of the subcarrier and manages to completely log to the frequency and phase of this subcarrier. By the way, I should also mention that as often happens, people have found shortcuts to decoding the signal. Especially the recording from GBT has such a great SNR, meaning the signal is very strong because GBT is a very large telescope, that it's not necessary to log to this carrier. You can just look at any one of these data side lobes. Of course, by doing that, you lose 50% of your signal power because by looking to this carrier, you manage to combine the information in the two, which is the same, really. That's a question which comes often. At the same time, both of the subcarriers are transmitting the same information. It's just split in two parts. Each of those gets 50% of the signal power. And the reason is just because it's simpler to split it in two pieces than in one piece. You could imagine this one not being present and only an upper subcarrier. So that's more complicated to deal with than having two subcarriers. So that's the reason we have two, but then we need to combine them back. And people have done shortcuts. They don't combine the subcarriers. They just look at one of the subcarriers. They do this Costas loop to recover or to correct for the effect of the Doppler, and they are good to go, basically. So yeah, coming back to that, I'm going to disable this part of the flow graph because it's a whole another world, and we will play this and do a couple comments on what comes. So here we can see the spectrum of the signal, nothing new. This is the same as we saw on the waterfall. And if I zoom in and look very closely, this, by the way, is being played back in real time. I have a throttle block so that the playback is one-to-one with respect of real time. I just do this for demonstration purposes and also not to use 100% CPU on my computer. If I wanted to process the recording as fast as possible, I would disable that throttle block, and then I wouldn't need to wait for 35 minutes for the whole recording to play back. So as you can see, the frequency of the signal is decreasing because of Doppler. Then in this plot, we have the PLL output, and the PLL output has accomplished two things. The first thing is the central carrier has moved to 0. So we can zoom in very closely here. And this is 0 and it doesn't move. I can make a comparison and zoom into both. And this one is moving, this one is not. So the PLL is tracking the frequency movement and compensating for it. The second thing we notice is that the residual carrier is depicted in blue. This means the I part or real part of the signal. The data subcarriers are depicted in red. That means the imaginary part or Q component of the signal. And this separation between the real part and imaginary part, between blue and red, is what allows us to combine these two subcarriers back and obtain this 50% signal to noise ratio gain, compared to processing just a single of those. Next thing we have is called the constellation diagram. So this is the output of the symbol synchronization. What we plot on a constellation diagram is the symbols. The symbols are the way in which binary digits or bits, which are 0 or 1, are transmitted as analog values. Here, -1 and +1. And we have these analog values and we also have noise. So all this bunch of points represents the 1 bits that were transmitted, the bits with the value 1, and they have moved from the ideal location and spread in this cloud because there is noise on the signal. And these are the bits with the value 0. Same thing has happened. What I mean by GBT recording being great is that these two cloud of points are completely well separated. It's perfectly possible to draw a line in the middle and say everything that falls on the right of this line is a 1, everything that falls on the left is a 0. If you look at the weaker recordings from the Allen Telescope Array and Medicina, you will see that these clouds are more close together, and then they start to merge in the middle. So then it's not so easy to tell if something you see here is a 1 or perhaps it's a 0 that has too much noise and has crossed over. That means that when you draw this vertical line and say everything on the left is a 0, everything on the right is a 1, you are doing some bit errors. There are some bits which have flipped along the way in your decoding process. So that brings me to the next topic, which is error correction. Let me close this. So for error correction, as I was explaining in the beginning, there are many mathematical algorithms we can use, and something magnificent about our knowledge of error correction is that we have algorithms which perform quite close to what is possible according to the laws of physics and mathematics. Pretty much none of our other technologies comes to such an extent where it is already limited by physics. For example, rocket propulsion, we know we are orders of magnitude from what physics allows us. It's just really difficult to design rocket engines. You need a lot of propellant. So there are all sorts of technical limitations to designing better rocket propulsion. But yeah, physics allows you to accelerate a small mass to close to the speed of light, and so get a very well-performing rocket engine. We just don't know how to do that. On the other hand, error correction codes, we know how to approach very well the laws of physics. Those are called capacity achieving error codes. And of course, for deep space communications, we tend to use those codes because the spacecraft are really far out, and the science people want to send as much data as possible from their instruments. So TGO uses one of those codes, which is called a turbo code. And coming back to the SETI topic, the choice is between using when trying to communicate to an alien, which doesn't have a common understanding of what codes you use. The choice is between using something really simple, such as repetition coding, or no coding at all, and then that performs very poorly, or something really complicated, such as turbo coding, which performs very close to the laws of physics. So anyhow, for decoding the turbo code, and this is not encryption, this is just error correction, we need something which is called a turbo decoder. The open source implementations of the turbo decoder that I'm aware of, either the one here in GNU Radio or the one that you can use with SIGDigger or with SatDump, are fairly slow. So depending on the number of iterations that you need to do, and this has to do with the signal to noise ratio. So for GPT, we can do one iteration and that's fine, but to decode the Allen telescope array, we might need to do maybe 5 iterations or 10 iterations. So depending on the number of iterations, this can get really slow. And for processing the whole file, it might take a couple hours, 4 hours. Even I was decoding this smaller station on the Azores Island, and it was a longer recording they did. So with 20 iterations, that took me overnight. So yeah, that's to be expected. But with GPT, you can do one iteration, and at least on my computer, it takes, I don't know, maybe 30 minutes to decode the whole file. So what else? Turbo coding works in frames, which are the basic units of error correction. And when we are looking at this signal, we see a stream of bits, ones and zeros. Those are shown here in blue. So we need to have a way to tell where the frames begin and where they end. And this is achieved by using something which is called the attached synchronization marker, which is simply a 64-bit sequence, which is fixed and well known, that is sent before each of the code words. doing some mathematical procedure which is called correlation, and is used to find a particular pattern on a sequence. We can look for that attached synchronization marker and plot the places where the attached synchronization marker can be found. And that's shown here in the red plot. So you can see these spikes, these correspond to locations of the attached synchronization marker. They are obtained with this correlation. And the stuff which is between each of these two is one of these code words. So what is happening at this stage is that the receiver is finding these attached synchronization markers, is selecting the bits between them as if I were to do some kind of selection like this, and it's sending those bits to the turbo decoder, which is then doing some clever statistical analysis to try to figure out, given what we have observed in the signal, what would be the most likely message that has been transmitted, even if there are some errors in what we observed. So that's how error correction works. And by the way, I don't think anyone has done this in Discord, but there's a shortcut. These can be skipped as well, because the error correction code is systematic. That means that the original message is enriched with more information rather than completely changed. So to the original message, more bits are added, and actually the same amount of bits are added. Maybe I will say it in another way. Each of the bits I'm looking at is one bit from the message, original bit from the message. And when I say message, I don't mean the assigning space message. I mean all the information transmitted by TGO, be it usual telemetry or be it part of the assigning space message. So all that digital information, it's every other bit is digital information. The next bit is error correction information. So by taking out only those bits that are part of the original digital information, you can completely skip this error correction step, given that GBT's recording is so great that there are no errors. So anyhow, that's for the error correction. I'm going to take a look at the chat because there are a couple of questions or comments. Feel free to also make comments in voice at this stage. Yeah, good point. I mentioned that for assigned space, we worked with ESA to reduce the rate at which the data is sent for the ATA to be able to receive the signal. So usually TGO transmits at a much higher data rate between, I think, 0.5 million bits per second and a few million bits per second, maybe 5 million bits per second. Who knows? I have the exact value somewhere, but I forget. So when they transmit at that much higher data rate, they do not use this kind of modulation with a carrier in the middle and the sidebands, because you can imagine that the bandwidth of these sidebands is proportional to the data rate. So if I have a huge data rate, I have huge sidebands. I also need to have a larger separation here. And what happens is that the X band is very crowded. It's only 50 megahertz. All the deep space spacecraft share them. And there are a bunch of spacecraft on Mars. So up to the point that radio frequency interference between several spacecraft on Mars is starting to become a problem in some very specific situations. So spacecraft are limited in the bandwidth they can use. So then for transmitting a higher data rate, what they use is to use a different modulation, which doesn't have this and just looks like one of these. And then that means that you do not have this very narrow band peak. So it might, it is more difficult to detect both from a SETI perspective or from a amateur radio observator perspective. Anytime you don't have a large enough dish or you don't know the kind of signal you're looking for, it will be much more difficult to detect if it doesn't have this narrow band theater. So that's it. What else? Yeah, the other thing I wanted to show is while the turbo decoder is running, we are getting the frames being decoded in hexadecimal, and those go to a binary file, and this binary file contains all the digital data that was transmitted by TGO. Among this data, there is the so-called idle data, because as you have seen, the spacecraft signal is present all the time, but sometimes the spacecraft doesn't have any information to send out. Maybe you can think of about the Ethernet card on your computer. It has a LED, an LED that blinks when you send a packet. But still on the Ethernet cable, there is this Ethernet signal present all the time, even if you're not sending packets. So this is more or less the same. You have the radio frequency signal, which is present all the time. And when the spacecraft has some data to send, it sends a non-idle frame. When there is no data to be sent, it sends an idle frame, just because frames need to be sent all the time to keep this radio frequency signal active. So yeah, there is this idle data. There is also non-idle data, which is usual data coming from the spacecraft. And there is also the assigning space message, which was transmitted in the only way it can possibly be transmitted with this TGO spacecraft. What else should I mention? Yeah, protocols. People have been really efficient in locating the documentation for protocols. So these are I should mention CCSDS. So there is a standards body which is called CCSDS, and they make standards, or rather recommendations. As you can see, it says recommended standard. So that means there are still some flexibilities, some choices that spacecraft designers can make. You won't get all the values just by reading this, but at least you will get some ranges of values or some arrangements, and then you can find the values you're missing by observation of the signal, by trial and error, or whatnot. So people have located these TM synchronization and channel coding. So that's basically the format of these frames, and the first bytes are a header, which tells you what is the spacecraft identifier that points to a particular number, which is used by TGO. Where data begins here, what's the virtual channel, and useful data goes in a virtual channel. Idle data goes in a different virtual channel so that they can be easily separated at the receiver. And then what happens is that this is not very convenient for communications, because as you might have noticed, the frames here have fixed size. They have 1,113 or 15 bytes, depending on whether you strip the CRC or you don't. Here I'm removing the CRC. People in Discord have preserved the CRC. That's just a matter of convenience. Just take note that there is a CRC you can check to make sure that the turbo decoder hasn't made any errors. So that's not very convenient, because I mean, here in a fixed size frame, the size is fixed, and oftentimes the stuff you want to transmit doesn't have a fixed size. So there is something on top of this TM protocol, which is called the Space Packet Protocol. And that's used to send packets of variable size. And the way it works is basically on the payload of the frame. So that's everything except for the first 6 bytes, which are header, and the last 8 bytes, I think, which are footer with some control information. Everything else, you can think of it as a continuous stream of information in which you have space packets arranged back to back, as if it was some kind of sausage. And the way to know where the links of this sausage are, or where the space packet boundaries are, is because of something here in the header called first header pointer, which points at the beginning of the first complete space packet within the payload. Let's pretend it's here. And then in the space packet header is the first 5 bytes of the space packet. You have the length. So let's pretend it's this. Then you would say, oh, okay, this is the length of the space packet. So it begins here, of course, and it extends up to here, and it ends maybe there. So the next thing is the next space packet, and you continue in this way. And when you run out of data, you move on to the next frame. So that's how you recover the space packets. And that's how people have done. If you look attentively on Discord, you will see some C code. Mainly people are doing C for this, where the frames are read in a binary file, and this sort of procedure I've mentioned is done to extract all the space packets. And then space packets are written to a file, and they've also seen a version of space packets on a CSV file, so you can open that in your text editor in Excel or whatever, and classify. Questions at this point, because there's only 5 minutes left. Okay, another important comment so that you can follow along what's going on in the Discord. In the header of the space packets, there's something which is called application process identifier, or in short, APID. The APID is used to distinguish between different types of packets or different types of applications, or packets being used for different stuff. You might imagine that DGO has different science instruments, so data from different science instruments will go in different APIDs. It will also have technical information, maybe voltages from solar panels, so that might go on another APID. Science space message might go on another APID. So that's the way that you separate easily between data of different types or different instruments or whatever. If you know about TCP/IP, in TCP/IP you have ports, and for example, this is HTTPS. So HTTPS is port 443, and that's how you separate between your different applications. So APID is more or less the same, but there is no such thing as a standard list of APIDs for all missions. Each mission will use their own choice of APIDs, except for a few APIDs which are more or less standard. For example, APID 0 is for the time service. That's basically to send the spacecraft clock. It's sending the current date and time according to the spacecraft clock periodically. So that goes on APID 0, and that's quite standard, and people have shared that information in Discord. Okay, comments, questions? Probably stop sharing at this point.
Yeah, thanks a lot, Daniel, for this overview. It's been really great. Excellent. I'm not sure if you ended up sharing the Zoom link with people, but I think now I know that it's being recorded. Maybe we can share that. Maybe we can share the recording. I guess that's something we can do, and then leave people ask questions and such on Discord.
Yeah, of course. This is being recorded, so the people who have found that the event was sold out will be able to watch the recording. And I'm following along daily on the Discord, so feel free to add me there or ping me with any sort of questions you have, either if you have watched this live or if you are watching the recording later on.
Sweet. All right. Well, thanks everyone for tuning in, and thanks everyone seeing this recording later on. Again, if you have questions, please refer to Discord, and we'll try our best to go through the questions there. Apart from that, thanks Daniel a lot for again for the excellent overview, and I hope everyone has a great evening, night, or morning, I guess, depending on where you are. Thanks everyone.
Thank you, Wael, and thank you everyone for attending. See you in Discord.
See you there.